In the previous video, we learned what is proof, and next, we introduce 4 basic proof methods we can use to prove a theorem to be true. And they are direct proof, proof by contraposition, proof by contradiction, and proof by cases. I will focus on theorems of implication forms because implication form is the most common form of theorems. For the direct proof, there's really no other tricks. You only need to show if the hypothesis is true, then the conclusion must be true. You can use all the axioms definitions and all the theorems you had proved before. In addition, you can also use the inference rules we learned from predicate logic. Let's look at 2 examples. The first one, if n is odd, the n squared is odd. How do we prove this one? Usually, we can think about the definition of the hypothesis. It says n is odd. What is the definition of an odd number? We all know that a number is odd if it's not divisible by 2, correct? In other words, if you want to represent an odd number, you can write any odd number as n equals 2k plus 1, where k is some integer, right? For example, 3 is equal to 2 times 1 plus 1, or 7 equals 2 times 3 plus 1, correct? So you start from here. And how do we show n squared is odd? Similarly, if you can write n squared equal to 2 times some integer plus 1, then you are showing that n squared is odd. So that's our target. How do we do that? Since you already know n equals 2k plus 1, you can just substitute n into n squared. Then you have 2k plus 1 squared, which equals 4k squared plus 4k plus 1. Okay? But they are not done yet. You want to transform this into this form. Of course, you can just factor out a 2 from 4k squared and 4k. This is the proof. Second example. If m and n are both perfect squares, then m times n is also a perfect square. We say an integer is a perfect square if it's equal to the square of an integer. For example, 9 equals 3 squared. So 9 is a perfect square. And 25 equals 5 squared. So 25 is a perfect square. Now we know the definition of a perfect square. Let's see how we can prove this theorem. The hypothesis is m and n are both perfect squares. The conclusion is m times n is also a perfect square. Again, we'll start from definition because that's the only thing we have now. And since m is a perfect square, we know that m can be represented by s squared, where s is some integer. Similarly, since n is a perfect square, n can be represented by t squared, where t is some integer. And in order to show mn is also a perfect square, we have to show mn equals some integer squared. How do we show that? Well, you already know how to represent m and n. You can just substitute them in. You have s squared times t squared. Then you can factor out this squared operation. You have st squared. So now you can conclude Mn is a perfect square. This is another exercise. You can work on this after watching this week's videos. The second method is proof by contraposition. Again, remember, we focus on the theorems of implication forms. Now, instead of proving P implies Q directly, we prove this implication. But why can we do that? This is because of the implication law. Remember what this is called? This is called the contrapositive of the original implication. And by implication law, we know these two are logically equivalent. That's why we can prove not Q implies not P instead of proving P implies Q. But some of you may ask, why does it help? Why we prove not Q implies not P instead of the original implication? This is because sometimes if you start from the hypothesis, it may not be easy to see how to prove the conclusion is true. We'll see two examples next. First one, for any integer n, if n squared is even, then n is even. For this implication, if you try to prove it using direct proof, and you start from the hypothesis where n squared is even, we know that by definition, your even number can be represented by 2 times k, where k is some integer. In order to show n is even, you have to be able to represent n by 2 times some integer. Now, we don't know how to go from n squared to n. Well, some of you may say, why don't we just take the square root? N equals square root of 2k. But now, how do we proceed? Even if you factor out a 2, you have this one, correct? And you have to argue why this one is an integer. But with contraposition, what you can do is, instead of proving this original implication, you can prove its contrapositive to be true. What is its contrapositive? First, we know this one is P, this one is Q. And we know its contrapositive is not Q implies not P. And what is not Q? It is N is odd. And what is not P? It's N squared is odd. So now the contrapositive is this one. Does this look familiar? Yes. This is the first example of direct proof. And we know how to prove it. And therefore, since you proved its contrapositive is true, we can conclude the original theorem is true. Second example, if 3n plus 2 is odd for any integer n, then n is odd. Similar to the previous example, if you want to prove this theorem using direct proof, you start from 3n plus 2 is odd, so it can be represented by 2k plus 1, where k is some integer. Then, in order to show n is odd, you have to be able to derive n, which equals. Then we run into the similar problem, which is it's hard to argue why this number is odd. Therefore, what you can do is we can use proof by contraposition. So this is P, this is Q, and not Q is n is even, and not p is 3n plus 2 is even. And since n is even, we know n can be represented by 2k, where k is some integer. Next, let's substitute n into 3n plus 2, which equals 6k plus 2. Then you can factor out 2 to have 2 times 3k plus 1. Then since k is some integer, 3k plus 1 is of course some integer. Therefore, you show that it's 3n plus 2 equals 2 times some integer. So you can conclude 3n plus 2 is even. And therefore, you prove that the original statement is true. Third example. If r is irrational, then the square root of r is also irrational. For this one, if you want to prove it using direct proof, then we don't know how to represent an irrational number. Therefore, we use proof by contraposition. So this contrapositive is if the square root of r is rational, then r is rational. Why do we do this? Because we know how to represent a rational number. The definition of being rational is a real number r is rational if there exists integer p and q, where q is now equal to 0, such that r equals p over q. And since the square root of r is rational, by definition, we know it's equal to p over q, where q is now equal to 0. And in addition, p and q should not have any common factors. What about r? R is equal to the square root of r squared equal to p squared over q squared. And since both p and q are integers, p squared and q squared are both integers as well. In addition, since q is not equal to 0, q squared is not equal to 0 either. So we show that r is a rational number as well. And thus we can conclude the original theorem is true. Here is an exercise for proof by contraposition. You can work on this after watching the videos. So far, we have introduced the first two basic proof methods, direct proof and proof by contraposition. In the next video, we introduce the last two basic proof methods, proof by contradiction and proof by cases.